Assalamualaikum and hello to everyone. In this video tutorial, we will look at one question from chapter 6 involving the diesel cycle. So in this question, we have a diesel engine which has been designed to have a compression ratio of 16. So RV here is 16. The air is compressed at 27 degrees Celsius and 100 kilopascal at the beginning of the compression process. So the values for 27 degrees Celsius here is for temperature at state 1, and the pressure of 100 kilopascal here is the pressure at state 1. The maximum temperature of the cycle is 1300 degrees Celsius. So the maximum temperature occurs at state 3. So this is the temperature for state 3. Okay, so sketch the cycle on a PV diagram and determine A, the temperature in degrees Celsius, and the pressure in units kilopascal at each of the processes, at the end of each processes, and then B, the net power output in units kilojoule per kg. So in other words, lowercase w net, and then the thermal efficiency in percentage, so the thermal efficiency, and finally the mean effective pressure in units kilopascal, so MEP. Okay, so given in the question are the constant for the working fluid, the values for Cp, Cv, and the gas constant R, and also the specific heat ratio gamma or K. Okay, so let's begin to solve the question. So for step 1, okay, if we do not want to draw the schematic diagram, we can always draw the PV diagram for the diesel cycle. Okay, so we have here the the PV axis. Okay, so for a diesel cycle, state 1 is the lowest state, isentropic compression to state 2, and then the constant pressure heat addition to state 3, and then the isentropic expansion to state 4, and finally the constant volume heat rejection to state 1. Okay, so this is the PV diagram for the diesel cycle. Okay, next we can go to the step 2. So for step 2, try to write what is required or any equation that we are going to use. So for A just now, we have to find the temperature in units Celsius and also the pressure in units kilopascal at the end of each state. So from the question, we already have the temperature at state 1, which was 27 degrees Celsius, and also the pressure at state 1, which was 100 kilopascal. Okay, so for state 2, we don't have the temperature, so we have to calculate, and also we don't have the pressure at state 2. For state 3, we do have the temperature, which was 1300 degrees Celsius. For pressure at state 3 is the same as the pressure at state 2 because the process is a constant pressure process. Okay, so the pressure for state 3 is the same as the pressure at state 2. And finally, for state 4, okay, we do not have the temperature and also we do not have the pressure at state 4. Okay, so which one we do not have, we have to find in step 3 later. So this is step 2. Okay, so for B, the question asks us to find the net power output. So W net, lowercase letters, is equals to the amount of heat added minus the amount of heat rejected. Okay, so we can expand the equation. So for Q in, or amount of heat added, is equals to the specific heat constant at Cp and then the temperature at state 2 minus the temperature at the temperature at state 3 minus the temperature at state 2. For amount of heat rejected, it's the specific heat for constant volume CV multiply with the change in temperature from state 4 to state 1. Okay, so we have to calculate it individually, and then we can solve for the amount of net power produced. For C is to calculate the thermal efficiency. So the equation for thermal efficiency, okay, is the amount of net power output divided with the amount of heat added. Okay, so we just have to substitute the values which we have already calculated previously. And for D, we have to calculate the mean effective pressure. So since we have calculated the lowercase work net, so we will use the equation lowercase work net divided with the specific volume at state 1, which is the maximum specific volume, minus with the specific volume at state 2, which is the minimum specific volume. Okay, so we can find for the mean effective pressure. So once we have all the equations which are required, so we can find the respective properties. So now for step 3, okay, is to find all the required properties. So for state 1, okay, what we have are the pressure, the temperature, okay, which was 27 degrees Celsius, but we have to add with 273 to change it into Kelvin. Okay, why? Because we have to calculate for the specific volume at state 1. Okay, so specific volume at state 1, we have to calculate it, so we can use the ideal gas law. P1 specific volume 1 equals to RT1. Okay, so the specific volume at state 1, okay, we can substitute the required values. And we can calculate for specific volume 0.861 meter cubes per kilogram. Okay, so at each state, try to find the pressure, the temperature, and also the specific volume at each state. Okay, so next we go to state 2. Okay, so for state 2, okay, we know that from state 1 to state 2 is the isentropic compression. So the compression ratio, specific volume 1 over specific volume 2 is 16. Okay, so from here we can calculate the specific volume at state 2. Okay, so substituting the values, okay, we can get the specific volume at state 2 as 0.0583. Be careful of the decimal points. Okay, be careful of the decimal points. Alright, next is to calculate the temperature or pressure. Okay, so we can start by calculating the either one. Okay, so let's say if we want to calculate the temperature first, so we can use the isentropic relationship equation between state 2 and state 1. Okay, and then we can solve for temperature at state 2 by substituting the values, and we can calculate for T2 here, which is equals to 909.4. And then we can solve for pressure also using the isentropic relationship equation between pressure and also specific volume. Okay, so we can solve for pressure at state 2. The pressure at state 1 was 100 kilopascal. So we can get the pressure at state 2 here as 4850.3. Okay, so we have already calculated for the pressure and the temperature just now. Since the question asks us to find in units Celsius, we have to minus it with 273. Okay, so we can get here, okay, 6, okay, 600 and 636.4, okay, degrees Celsius. Okay, next we go to state 3. Okay, so state 3, okay, we already have the temperature 1300 degrees Celsius, but for calculation we have to change it into Celsius, in Kelvin. Okay, so to solve for pressure, okay, to solve for the pressure at state 3, remember constant pressure process, so the pressure at state 3 is equal to the pressure at state 2, so the value is the same. Okay, what we have to calculate now is the specific volume. Okay, so using the ideal gas law, okay, so we have to calculate for the specific volume. So 0.287 multiply 1573 divide by 4850.3. So we can get here 0.0931 meter cubes per kilogram. So now why do we have to calculate the specific volume at state 3 is because we have to know the cut-off ratio. Okay, the cut-off ratio RC, which is equals to the specific volume at state 3 over the specific volume at state 2. Okay, so 0.0931 divided by 0.0583, which gives us roughly around 1.6 if we round up the decimal points. Okay, so there are no units for cut-off ratio, so 1.6 is the cut-off ratio. Okay, next we proceed with state 4. So for state 4 here, okay, we don't have the temperature, we don't have the pressure. Okay, so we have to calculate. So to find for pressure or temperature, we have to use the we can use the isentropic relationship equation for gases involving state 3 and state 4. Okay, so let's say if we want to solve for the temperature, okay, we can use the isentropic relationship equation. Remember that V4 over V3 here is equals to the compression ratio over the cut-off ratio. So that is why we have to calculate the cut-off ratio just now. Okay, so we can substitute the values to find for temperature at state 4. So T3 was 1573 divided by the compression ratio over the cut-off ratio, 1.4 minus 1. So this will give us 626.2 Kelvin minus with 273. Okay, we can get 353.2 Celsius. Okay, for pressure, so for pressure we can use also the isentropic relationship equation, P3 over P4 equals to V4 over V3, the specific volume, by the power of K. Okay, so P4 here is equals to, the pressure at state 3 just now was 4850.3 divided by the compression ratio over the cut-off ratio by the power of 1.4. So this will give us 193.1 kilopascal. Okay, so we have calculated all the required properties, so we can then proceed with step number 4. So for step number 4, for the first item A, okay, which was to find all the temperatures and pressure at the end of each state, so this has been solved in step 3. Okay, so for B, which is to calculate the net power produced, okay, we have already written the equation just now, so we have to calculate the amount of heat added individually. Okay, in units Kelvin. So we can get the amount of heat added as 666.2, sorry, 0.92 kilojoules per kg. For amount of heat rejected, Q out, we have written the equation just now. So we can substitute the values. T4 was 626.4 Kelvin minus with T1, so we can get the amount of heat rejected as 234.21 kilojoules per kg. So the amount of net power produced, W net, is equals to the Q in minus Q out, so we can calculate and we can get the answer as 432.71 kilojoules per kg. Okay, for C, which was to calculate the thermal efficiency, so the amount of net work produced divided by the amount of heat added, so 432.71 divided by 666.92, which gives us around 0.649, which is 64.9%. And finally, for D, the mean effective pressure is the amount of net power produced divided by the specific volume at state 1 minus the specific volume at state 2. So 432.71 divided by 0.861 minus 0.0583. So this will give us 536.1 kilopascal. Okay, so this is a question for diesel cycle from chapter 6. So thank you for your attention and have a good day.